So, welcome to the stream. Today I will work on this root.io package. Yeah. This is to read data from the CERN root file format. And yeah, it's based on Julia. It's a native reader. And I'm recording this just for fun. Let me check if the stream is working. It will start in a few minutes. Don't expect too much action on this channel. It's just tinkering. I will read a lot of docs. I will stare in the camera or on the screen and do nothing for like a few minutes and then type something and then wait again. So it will be quite boring, but if you are bored too, you can just watch, comment, whatever. And of course, if you have any ideas how to do it better, or if you have any questions about my setup or what I'm doing, just feel free to ask in the chat. I try to watch it. How can I open the chat? There we go. So, I think sound is working. Yeah, it seems so. I will shut it down on my iPad. Yeah, it seems so. I will shut it down. Yeah, so currently I'm trying to read out jagged arrays in baskets. It's quite annoying. I have not fully understood how root stores jagged data in baskets, but fortunately Jim helped me a lot to understand this. So let me check. Where is my browser? There's this really nice Google group. So if you are curious about the root data format, feel free to check this out. So this is actually the structure. You read this T key, and then you have this content, f last minus f keyland, and then you have 4 bytes, whatever, 4 bytes. So what these 4 bytes are was mentioned by Philip G. Canal. So the first X is a flag that indicates the type of data that follows. This is in T baskets at line 919. And then, so if it's greater than 80, then the new optimization to skip storing the offsets array was used. Okay, and then the second X, which in Jim's scheme is this one, 4 bytes. Is metadata pointer to location of last used byte in basket. So let's put this into the code. This is this one which I skipped. I just make a comment for now. Let's think like this. I don't care. Maybe I also put a reference in to this forum, just you can find it again. Yeah. Of course, I should announce the stream in the Julia channel if anyone is interested. So Julia Lang. I always forget this like Julia. Is it this one? Ah, let's go this way. Oh, come on. Julia Lang, of course. And I need the link. Where's the link? Miguel had a stream yesterday. It was quite nice. I was watching it a little bit, not too much. Right, so this is the link. Stream started right now. Yes. Okay. So let's see what we do. Okay, let's go a bit larger on the screen. Oh, let's go like this. All right, so offset length. So one problem I had is with uncompressed datasets. This is a bit interesting. Let me open a file. So I have this alias Julia P, which is just Julia -- project equals dot. This means this will start a Julia session with the current project activated. So you might know that this will read the project toml, etc. Yeah, like this. And Julia T is the other one, which will run the test. So this will activate the project and run the test, so that I can make sure everything is working. This no OMyREPL installed is coming from my Julia RC. There I usually load OMyREPL and revise, but on this machine OMyREPL is currently not installed. I had some glitches, so I just deactivated it. It made my workflow a bit slower, so I basically had to deactivate it to be a bit faster, because if you launch the Julia REPL all the time and exit and launch again, etc., then you want to save every second you can, and this OMyREPL took like 5 seconds to load. Alright, so Julia P, let's see how this works. I'm gonna split my screen. So I have the streamers and the streamers.jl, and this is basically the current user API you do using root.io. Which we now recompile, and then you open a file with this this function. Let's look at some online files from CambStreamNet. This is, by the way, the experiment I'm working on. It's a neutrino detector, and I'm doing online event reconstruction, and I desperately need a reader for root files, because I wrote my whole reconstruction algorithms in Julia, and this stuff is running live, And I'm parsing the live binary stream, the network stream from the detector, which works fine, and we have all kind of specifications of this format, so it was very easy to implement it in Julia. It's just basically a few structs which you need to define, and some high-level network protocol on top of it, which is based on the control host and Ligier protocol implementation. So it was used for Antares in the former detector, and then some other experiments. So yeah, nothing special. But the problem is, of course, if you want to run your reconstruction on Monte Carlo files, on offline files, then you need to parse these freaking root files. And these, of course, have another format. All right, so you can have a look at the keys of this file. You see that we have several streams, several directories. This is basically coming from this root file. And if I look at the KM3net event, where we store all our event data, this will return a root tree, a T tree. So this parsing works already. This root tree also have keys, so you can look at these keys, and there's another nested element which is also called KM3net event. So let's get rid of these keys and look at this element. This should be a T. Oh no, it's missing. Of course, it's singular. Yeah, so this is a T branch element, and this T branch element, then let's look at the keys of this. You see that there's the duck preamble and duck event header, triggered hits and snapshot hits, and I'm mostly interested in these snapshot hits. This is basically the branch I want to read out. So if you want to read out a branch, currently the root IO, you say give me an array of the file, and then you give it the path, which is basically KM3net event / KM3net event / snapshot hits, and that's it. This will error now because it says it cannot understand a T-leaf element type. The element types are basically read during runtime, and these structs are constructed during runtime. And currently I implemented it like this, so it will basically require this to be defined. If it's not defined, I get an error. So I know that I need to define some kind of parser for this specific type of streamer. But what you can do is you can provide the raw equals true keyword, and then you will get the byte. The only problem is that it will return the raw bytes of this baskets, basically, from this branch. But this is jagged data, so this means that in this snapshot hits you have some items. This is basically a vector of vectors, and this second array should tell you where the vectors basically begin and how long they are, given the difference or so. But these numbers are obviously wrong. There should be some smaller number in this case. And yeah, this is what I'm trying to figure out right now. If I open another file where I'm reading some offline data, let's look at offline data. I looked at some triggered hits. This is, for example, the DOM ID for all the hits. And there you see the offsets are fine. So this is basically an array which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 subarrays. And the data of the subarrays start at 75, byte offset 75 to 779, and then 779 to 1279, etc., etc. So this way you can read out all these stuff. Actually, this one probably goes to the end. I have to check this out. Anyways, here we are able to read these offsets correctly. This is probably related. So I think I have some problems reading the other one because it is uncompressed. So funnily, the compressed version works and the uncompressed one does not. So here you see the offsets are kind of rubbish. I expect some monotones, some monotonely increased numbers. These are not so. And if I enable debug mode, here you can see that this is an uncompressed data stream. So I guess I did something wrong with the uncompressed readout, but I have to look at it. So uncompressed. This is coming from here somewhere, but it's actually a quite tiny function. So get the position of the file pointer. I check if it's compressed. If it's compressed, I return the IO. If it's not compressed, then I first unpack the header and then read all the stuff and return the buffer. So maybe I have to skip here some bytes. I have no idea. Just skip 10 bytes. Let's see what happens. Now it needs to recompile, thanks to revise. I don't have to reload the whole session. Okay, it's still rubbish data. Let's try with 6 or so. It changed something actually, so no, still not. Maybe it's 4. We are just now guessing. No, it's not 4. So yeah. Now we will probably have a look at the uproot implementation. Uncompressed. Let's see, basket data. Meanwhile, I have to read some emails. I'm sorry. Maybe I'm not sure how to proceed here. I have to. I think I will save the raw data now, and I will look at it in a hex editor. So this is what we get. So this gives me the. Actually, let's change this so that it returns the full array. It's in ROOTIO.jl. Content size. So instead of content size, we read until plus get key object length, and continue. Yeah, now you see this typical root header with this 00, 040, 0003. Okay, let's see if this data offset is now empty. So this is our data. So we have 3030 elements. Now let's look at it with our root, just out of curiosity. Let's activate the Python environment. Uproot, activate. So the data was uproot, open, test, samples. Came through online data. I have some debugging action here, so let's continue. Okay, got it. So and now we look at F. Actually, let's yank inside this one. So this. Okay, alright, cannot read it, so we need to do uproot as debug. Alright, let's save this as array. Okay, so what's the size of this? 310 elements, and here we have 330 elements, so this is 20 bytes more, and 20 bytes more is, I think, reasonable because you have 4 bytes. You remember this picture or infogram from Jim? So you have these 4 bytes and 4 bytes, and then the offsets, and I know that this particular file has 3 events, so I have 3 times 4 bytes in it, which is 12, and 12 plus 4 gives 20. So we should have 3010 elements, and the last one should describe the offsets. So let's save this into the file. I'll put it on my desktop. Let's call this, what was this, an event, internet offline. It's triggered, it's online, not offline. Dot in write mode. Oh dear. So, and then let's write data into this F object and close it. Okay, let's compare the bytes quickly. So array flatten the first 10 elements. So here are the first 10 elements, look like the same. 40 is 64, that's true. Then 3. Actually, we can do it better, right? Signed, broadcasting side, so we get the numbers. And I think that looks okay. Yeah, this will of course Okay, otherwise. So let's look at the end. Like this. So look at 80,000 until the end. Not quite, because we have 20 more elements, so let's add 20 to this. Oh no, this means I have to add 20 here. Huh. No. I have to subtract 20. Let's don't do the math, just type it down like this. I guess this doesn't work. What the heck? 317. I don't see the numbers matching. So here, these are the last 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. These 10 bytes should be right around yeah, it should be here. I don't understand. 24. Ah, there we go. 1, 2, 5, 10, 60, 33, then of course the unsigned, and then 3, 23, etc. Okay, but why is this? Ah, sure. It's just because of the indexing. So in Julia, you would type 3001. I'm not sure if I'm doing this correctly. So does this even work in Julia? No, it doesn't work. Okay, data. But the first 3010 elements should match. Maybe I can just check this here. So Julia data equals open. Let's open this users desktop game3net in binary mode and read. Okay, I think we can now somehow pass this to NumPy. NumPy array Julia data s type new int 8 in u1. Not s type, d type. Oh, how do you convert string from string? IP from string. Where's from string? Let's try it like this. Must be a multiple of element size. This. Okay, this looks okay. Oh, it's deprecated. So from buffer, right? Let's use from buffer just to be conform. From buffer. All right. Ah, yeah. Now I know what's going on, because if you look at the data from uproot, it already got rid of some stuff at the beginning, and I think this is. So we'll write this. So Julia data, and then we have this uproot data. Okay, we see some differences, and I think I need to shift the uproot data by 10 or so. No, was it 4? Oh, not again. Okay, yeah. Julia data, uproot data. First 10. Okay, so the Julia data has already 1 extra byte at the beginning. Why ever? Why do we have an extra byte? This may be already the answer. Compressed. Let's return the data. No. Ah, dear. That was dumb. Ah, the offsets are still wrong. Okay, let's have a look at the end of the data. So we look at the last 30 elements, and from uproot, the last 30 elements, and this should be the same. One off again. Holy shit. But these are the actual numbers I need. 0004, 00078, etc. I think these are actually the offsets. This is a flattened one. It's called R. Offsets. Zero 00433. Is this 970? Okay, we didn't get too far, so I don't know. But this basket key is correctly working. For now, don't need offsets. So this is what we get back. Let's get rid of the skip. Where did I write this? Types. Yeah. Okay. This always confuses me. So this is the end. So if you skip the first four bytes, this is this one. And the next 4 bytes is this one. That doesn't make sense. Yeah, so something is wrong with this damn uncompressed stream. And I don't know what. Okay, let's have a look at the data in the hex editor. So, the new file we were extracting is... Oh, it's not the grammars file, it's on my desktop. This one. No, we don't need to apply any grammar. So in this particular file, there should be some kind of a DOM ID. Ah, I see them here, I guess. Yeah, so we know from uproot that these numbers are stored somewhere at the end. So let's look for 970. I look for 970 as a 32-bit signed integer. And it's not in there. Oh, that's great. What about 2200? Oh dear. Is this somehow compressed? Then we should see an LZ, but it's not compressed. I see repeated data here, almost repeated. These should be our DOM IDs, I guess. Let's open another terminal. And go to KN3IO. Oh, it was already activated. Okay, ROOTIO. It's in test samples. All right. So this KN3IO is basically a wrapper library which uses uproot to map our data files in KM3net to uproot structures and make it more convenient to use, because we have tons of custom classes which are not as handy to access via the low-level uproot implementation. So we wrote some accessor classes which makes it easier to the user to navigate through our files. But essentially it's just uproot behind the scenes. So let's open the file with the online reader. KN3net online. Then we have these events. And we should have some triggered hits. Which way are you looking? No, you're looking at the snapshot hits. Oh dear. I'm looking here at the right dataset. Why I am talking about snapshot hits, triggered hits when I'm using the snapshot hits. Oh, here's correct. Okay, so I just called the file wrongly. Okay, alright. I take it back. The file name is just stupid. Okay, snapshot hits. Let's look at the shape. So we have 3 events. If we flatten this, we should have what? Ah, of course it's, yeah. Let's have a look at some dumb ideas. So we should see, for example, this number in the file. And it's there 2 times. Three times. Okay, so it's not compressed data. It's already something, already a good sign. So the data should be there. And how many occurrences do we have? So here we have like, yeah, I think these should be 2 hits. Like first, so a hit in KM3net is always 6 bytes. It's 1 hit. The first one is showing you the, let's open the data view. So the first bit is the channel ID, then you have the time, which are 4 bits. Here you see it's probably, oh, it's big endian. So these 4 bytes, oh, it's quite high. It's a bit confusing. And this one should be the TOT, the time over threshold. Anyways, this is another one. So these 6 should be a hit. And then you have here another, yeah, this is a DOM ID. When it starts with 80 and then blah blah blah, then it's most probably a DOM ID. Alright, so let's see if we can look at this first hit. Oh, we have 2 hits. DOM ID, channel ID. $10, $13, 0. So 10 and 13. Where's my? So this should be 10. Is it 10? Yeah, it's 10. And this should be 13. It's not 13. Why isn't it 13? Oh, sorry. This one should be 13. Yes, exactly. So DOM ID is this one. Channel ID is this one. Then we should see 26 and 19 when we look at the TOTs. 26, 19? Yes, exactly. And what about the times? Oh, they call it time. Yeah. So this is a bit tricky. I don't know why I see the same numbers, but the time should be this. Ah, there it is. It's a little endian, of course, why not? 307, 339, 18, that's great. And the next one is then, should be then 307, 339, 16. Let's confirm this. Yes, exactly. All right. So little endian. So this is the data. All I need is the structure. This is 1 hit. This is another hit. This is yet another hit, etc., etc., etc. That's all I need. And the question is, what is this data in front of? So this has a length of 11, which is very suspicious. I really think that this first byte should be skipped. Why ever? I have no idea. And then we have this usual 10 bytes to skip. And then we have this struct. Okay. So if anyone knows why there's a leading byte in uncompressed streams, yeah, Alright. Let's kill this buffer. Close this window. So where we go? So for now, where is this? Okay, this is the streamer. And we have this one. Okay, so it's in the data stream. So if it's uncompressed, I will now just skip one byte just for fun. So how many hits do we have? Oh, that's our array. Ah, damn, I have to look at it. Import through. I don't have this here. Split the window, open the terminal. Okay. Oh no. It's of course samples. F events. Snapshot hits. $298. So let's write a grammar for this just to have a feeling how this looks like. Let's close this. Okay, so we decided to skip one byte. All right, skip whatever. Then we have some kind of a binary structure, something like, okay, let's introduce a new structure. This is basically a hit, which has a number, an integer of length 1. This is our channel ID. We have an TDC time, which has a length of 4 bytes and is a little endian. And then we have the time over threshold, which is an integer of 1 byte. Okay, so this is a hit. Let's append a hit. So we now have, it's 1 byte. Okay, so the first hit, oh, that's completely wrong, because we need to skip the header. This is, I call this the T object header bytes, and this is always 10 bytes, most of the time 10 bytes, I guess. Okay, so the first hit is, oh, it's still wrong. Why is this wrong? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, of course. We first have the DOM ID. which is 4 bytes, big endian. And then the channel ID, and then the time over threshold. That looks good. All right, so this is our hit structure, and from these hits we have, in this case, we just hard-coded to 298. So let's make sure we have, these numbers look okay. You see that the time is, yeah, it's getting bigger and bigger. The channel ID is should never be more than 30. Yeah, I guess this should be fine. The TOT can exceed those numbers. So, and at the very end we now have 39 padding bytes. So we are missing, why do we have 39 bytes? I expected to have only 20. So something is wrong here, because here we still have some kind of a DOM ID. And then a hit. 1, 2, 3, 4, 5, 6, 7. And this is yet another DOM ID. And then 6 bytes. That's really annoying. It's also a bit worrying because I'm missing some hits here. This means this might even be a bug in KM3IO, or even in uproot. Channel ID, time, TOT. There's also DOM ID, channel ID, time, TOT. Oh dear. We are really missing. That's the wrong count. Yeah, I'm puzzled. Do I see this number somewhere here? I don't think so. Oh wait, maybe this flatten is not working correctly. Let's first check that. So this is the first. So we have 96. Huh. Let's set these numbers. Oh, that's correct. Oh dear. That's really interesting. So in KM3IO, it's in the online file, and I'm using this one as a readout. So it's snapshot hits. Maybe I made a mistake in this one. No, I don't think so. I think this is correct. I think I really have 300 hits here. All this is parsed correctly. So I need to find an issue in uproot, I guess. Ah, wait. No. I think I might have found the issue. There is... Maybe there is some header, because these are separated in 3 events. So the first event is after 96 hits. Let's see. Oh, this indexing is also a bit interesting. Why is it 2? Oh dear. No, everything's okay. Oh, here it starts at 2. Ah, what the... Okay, all fine. No, it's not fine. Why do I have to repeat it 300 times? It's still not okay. Okay, whatever. Let's have a look at item index 96 plus minus 1 or 2 or whatever. So 96. Let's see if these numbers make sense. Channel ID makes sense. TDC makes sense. Okay, here too. Oh, this doesn't make sense. There is no such term ID. Okay, so indeed we have some kind of a header at some point. So that's good to know. That's why we are missing here some files or some... Okay. Alright, good to know. So no bug. Just extended my understanding of the root format. Hallelujah. So after this So let's say we have a repeat of 96 elements. So this one should be not fine, because if we read the next one, it's broken, right? Yeah, this is rubbish. So after this, I just roughly guess we skip 10 bytes or so, and then we again read out the new hit collection, namely 124 times. Let's see how it goes. Yeah, that works. That works quite nicely. You see the DOM ID is starting with 80, that's fine, because all our DOM IDs are starting with this number in KM3net. Then the channel ID doesn't exceed 30. Okay, that's fine. The last element is then this one, which is now broken again. So repeat, you have to repeat it. But does this mean that we may have some problems with the last hit in KM3.0? Oh, that's fine. Okay, so that is parsed correctly in uproot. Whenever I think there is a bug in uproot, I find out that there is a bug in my understanding. It's quite nice. What still confuses me is why I need to repeat this. Oh, it's a bit confusing. Anyways, we have here now again, and let's call it hit 2. Let's repeat this 78 times. Whoa, where's my window? There's my window. So the next hit after this should be okay, indeed. And the last one should also be okay, indeed. So there we go. I think now we understand this freaking format. So we skip 1 byte. I don't know why. Then we skip 10 bytes because of the T object header, and then we have our structures separated by this T object header. Yeah. So this is how we parse the data. So if we now skip this one, 1 byte here, and let's have a look at this data again. Okay, so I will write a new file. Oh wait, data offsets equals snapshot hits. Yes. Let's call this snapshot hits. Okay, now let's open this data file. Snapshot hits. You can save this grammar. Save it in Dropbox, binary grammars, KM3net, online, snapshot hits. Okay, let's apply the grammar. Oh, this file is quite... what happened here? Data, offsets. Okay. Let's close this and close this. Open it again. Okay. So now, of course, no, that's the wrong grammar. Open the grammar. Okay. So now this should work, right? But still, I have only 19 padding bytes, and why? Why do I have only 19 padding bytes? Okay. Well, I need some food, so see you later.